Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly let me know in the chats with some fire emojis. Everyone. Good evening people, good evening and welcome back. Good evening and welcome back. So quickly, let me know in the chats if all of you can hear me, if I am perfectly audible and visible to every one of you. Yes? Right, people? I think yes, I am audible, visible. Perfect. So my dear students, as you all must be knowing, today it's going to be the second session of the chapter Chemical Bonding. Yeah? So before starting this particular session, let me ask you one thing. Are you guys done with the part 1 of chemical bonding? Say yes or no in the chats. Are you guys done with part 1 of chemical bonding? I would want you guys to let me know in the chats quickly if you all are done with the part 1. Yeah? Let me know quickly in the chats if all of you are done with the part 1 of chemical bonding. All right, I can see majority is done with the part 1. That's great. So today it's going to be the second session, second part. And my dear students, today's session we are going to start with one amazing concept from which questions are frequently asked when it comes to your NEET examination. And what is that? That is your Fajan's rules, right? In the last session, I showed you exactly how do we make the Lewis structures and how do we calculate the formal charge of different atoms. That's something which I told you in the last session, which was our first session of chemical bonding, right? And today, we are going to start the session with one more important concept that is going to be your Fajan's rules, right? And before starting Fajan's rules, the ones who have not liked the session yet, I would want every one of you to smash the like and do share this particular video with everyone whosoever is preparing for NEET 2025 or even 2026. These particular sessions, these quality sessions are basically for everyone. So I would definitely want you guys to share these videos with whosoever you know preparing for NEET 2025 or even 2026. I'll be teaching each and every concept here in the bonding. Yes, I'll be teaching VBT as well. Okay? All right. So let's get going then. Let's get started. And I would want you guys to take the note, whatever things I'll be writing on the screen, right? Take a note of every single thing, because every single thing which I'll be mentioning on the screen, that's going to be very, very, very important. Okay? Perfect. All right, people. So let's get going then. Let's get started with the Fajan's rules. Well. Before starting the Fajan's rules, before letting you know exactly why do we need the Fajan's rules, before making you understand the Fajan's rules, let me tell you certain basic things, okay, which I've already mentioned here on the screen. The first point, as you all can see, no bond is 100% ionic or 100% covalent. No bond is 100% ionic or 100% covalent. A lot of bonds, you know. A lot of bonds. For example, I'm taking a bond between H2, right? This is HH bond. Perfect. For example, I'm taking HCl. For example, I'm taking HF. Perfect. There is no bond as such which can be 100% ionic or 100% covalent. Every covalent bond will have every covalent bond will have some kind of ionic character in it, and every ionic bond has got some kind of covalent character in it. So there is no bond as such which will be 100% ionic or 100% covalent. Every ionic bond will be having some covalent character. Every covalent bond will be having some ionic character. And every ionic bond will have some covalent character. Right? Now, my dear students, as I told you, every covalent bond contains some ionic character and every ionic bond contains some covalent character. Okay? And these Fajan's rules, for what purpose we are going to study these Fajan's rules? Have a look on this particular point. My dear students, covalent character in an ionic bond, it cannot be calculated. It cannot be calculated, but can be compared. And for that purpose, what do we use? For that purpose, we use the Fajan's rules. So first of all, let me give you the brief idea of all the things, whatever I said. No bond is 100% covalent or 100% ionic. Every covalent bond has got some ionic character into it, and every ionic bond will have some covalent character into it. Okay? Right? My dear students, covalent character in an ionic bond cannot be calculated but can be compared. Right? And the Fajan's rules, which we are going to discuss right now, for what purpose we are going to study these rules? Fajan's rules are going to give us the idea about how to compare the covalent character in an ionic bond. So Fajan's rules is going to let us know how to exactly compare the covalent character, in an ionic bond, in an ionic compound. So that is the reason why we are going to discuss these Fajan's rules, which are very, very important. I hope you got to know why we are going to discuss these Fajan's rules. Fajan's rules, with the help of Fajan's rules, we are going to compare the covalent character in different ionic compounds. For example, I'll be giving you certain ionic compounds, and I'll ask you which ionic compound has got more covalent character, which ionic compound has got less covalent character. For that purpose, for the comparison of covalent character in an ionic compound, for that particular purpose, we are going to discuss these Fajan's rules. Okay? So Fajan's rules are going to be used to compare the covalent character in an ionic bond. Okay? Now, before letting you know what these Fajan's rules exactly are all about, I'm going to let you know certain basic things first. Then I'll move into the Fajan's rules. Write each and everything which I'll be mentioning on the screen. My dear students, imagine that you have got an atom A. Let's say I have got an atom A. Let's say this atom A, it contains 10 protons as well as 10 electrons. Let's assume that this atom A, it contains 10 protons as well as 10 electrons. Okay? So I can say something like this. These 10 protons are holding 10 electrons over here. Right? These 10 protons, they are holding 10 electrons over here. For example, imagine I'm taking one electron out of it. When I take one electron out of it, it gets converted into A positive. When I take one electron out of it, it gets converted into A positive. Since I'm taking electron out, I did nothing with the protons. It had 10 protons. Here also it will be having 10 protons. But how many electrons this A positive will be having now? Initially it had 10 electrons. Now it will be having only 9 electrons. Right? So I took an atom A and I'm assuming this atom had 10 protons as well as 10 electrons. Now what did I do? I took one electron out. It got converted into A positive. And this A positive, it has got 10 protons and 9 electrons now. Okay? Now, my dear students, if you understand logically here, over here, 10 protons were holding 10 electrons. 10 protons were holding 10 electrons. But right now, the same 10 protons, they are holding only 9 electrons. Initially, 10 protons were holding 10 electrons. Now, the same 10 protons, they are attracting these 9 electrons. My dear students, tell me one thing. In which of the case, A or A positive, where will be the electron experiencing more attraction? Where will be the electron experiencing more attraction? 10 protons were holding 10 electrons. Same 10 protons are only holding 9 electrons now. So can I say over here the electrons will be experiencing more attraction? Right? Over here, electrons will be experiencing more attraction. Right? So if I ask you, compare the effective nuclear charge of A and A positive. If I ask you, compare the effective nuclear charge of A and A positive. Can I say since the electron is experiencing more attraction here, I'll indirectly say effective nuclear charge of A positive is more as compared to that of A. Right? Due to the increase in the effective nuclear charge, here the electron is experiencing more attraction. Perfect. So my dear students, can I conclude one simple statement over here? Can I say, as the parent atom gets converted, into its cation, into the cation, effective nuclear charge increases. And as the effective nuclear charge increases, can I say indirectly, attractive power also increases? Absolutely, attractive power increases. Right? One simple statement which you are going to remember from now on. When the parent atom gets converted into the cation, its effective nuclear charge increases, therefore attractive power increases. Point number 1. Point number 2. Point number 2, my dear students. This was point number 1. Point number 2. For example, I've got an atom A over here. Imagine that it contains 10 electrons. Imagine that it contains 10 protons. So over here, 10 protons are holding 10 electrons. 10 protons are holding 10 electrons. Okay. Now, for example, imagine this atom A, it is accepting 1 electron and it is getting converted into A negative. Right? So this atom A, it accepted 1 electron. Initially, it had 10 electrons. Now the same will have 11 electrons. Did I do anything with the protons? I did nothing with the protons. Right now also, it will be having 10 protons. Now, my dear students, I think you already got to know what I'm trying to convey. I think you already would have got the idea what I'm going to say. 10 protons were holding 10 electrons. 10 protons were holding 10 electrons. The same 10 protons are holding 11 electrons now. So I would say electron over here in case of A negative will be experiencing less force as that of this A. I would say electron over here will be experiencing less force of attraction as compared to the electron of this A over here. Okay. What does it mean? Indirectly, I will say over here 10 protons were holding 10 electrons. But now the same 10 protons are holding 11 electrons. I'll say effective nuclear charge. If you compare the effective nuclear charge of A and A negative, I'll say effective nuclear charge of A will be more than that of effective nuclear charge of A negative. Right? Correct? Is it simple, guys? So when this A accepted 1 electron, it got converted into the anion. Initially, 10 protons were holding 10 electrons. Now, the same 10 protons are holding 11 electrons. So, I would say over here, electron will be experiencing less force of attraction as compared to the electron in A. Perfect. So, I can generalize one quick statement over here. What is that statement? I would say as the parent atom gets converted into the anion, effective nuclear charge decreases, and if effective nuclear charge decreases, I would say attractive power, what happens to that? Attractive power decreases. attractive power decreases. So more the effective nuclear charge, more the attractive power, right? More the effective nuclear charge, more the attractive power. Lesser the effective nuclear charge, lesser the attractive power. As simple as that. Okay. I believe these two statements are clear, right? Why these statements are important, you'll get the idea, you'll get their significance in some time, right? When I'll be discussing Fajan's rules with you. Okay. Now, my dear students, before moving on to the Fajan's rules, there's a term which I would want you guys to know. What is that? That is polarization. Have you heard about this particular term? Polarization. Polarization. What is this polarization exactly all about? What is meant by polarization? Understand. My dear students, polarization is defined as, in simple words, I'm going to define it. Polarization means the distortion of electron cloud. The distortion of electron cloud is something which I call as polarization. Now, what does that mean? What does that mean? Try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. My dear students, for example, imagine that here you have got a cation. Let's say this is the cation. Okay. And for example, here you have got an anion. And generally, anions are bigger in size. Generally, anions are bigger in size than that of your cations. Okay. Now, imagine that this cation, it started approaching towards the anion. Imagine that this cation started moving towards the anion. What will happen? See, I would say this is the electron cloud. This is the electron cloud of this anion. This is the electron cloud of this anion, right? If this is the electron cloud of this anion, can I say this cation, when it approaches towards anion, can I say this cation is going to attract this electron cloud towards itself? Yes, very simple. When the cation approaches the anion, what happens? The cation attracts this electron cloud of anion towards itself, due to which the electron cloud, which was spherically symmetric in the beginning, now it gets shifted like this. The electron cloud, it gets shifted in this direction. It gets shifted in this particular direction. When the cation approaches the anion, right? This cation is going to attract the electron cloud of anion towards itself, due to which the electron cloud of anion, which was spherically symmetric in the beginning, right? Which was spherically symmetric in the beginning, that got shifted in this particular direction. Okay? Or in simpler words, I can say, electron cloud of anion, which was spherically symmetric in the beginning, when the cation approached this, what happened? Distortion of electron cloud of anion took place. This distortion of electron cloud of the anion, when the cation approached towards it, this distortion of electron cloud is something which you call as polarization. I believe you got the idea of what this polarization exactly is all about. Yeah? Did you understand what is meant by the term polarization? So I would say this cation has polarized this anion. This cation has distorted the electron cloud of the anion. Okay? Right? Now, look at this particular statement, which is mentioned over here. When the cation approaches the anion, the distortion of electron cloud of anion takes place. And the phenomenon of the distortion of electron cloud right, of the anion, that phenomenon is something which we call as polarization. That phenomenon is what we call as polarization. So cation polarized the electron cloud of the anion. Number one. Now, due to polarization, what happens? Due to polarization, covalent character is induced in an ionic bond. Due to polarization, covalent character is induced in an ionic bond. What is meant by that? Just try to understand. This anion in the beginning was spherically symmetric. It was spherically symmetric. Now, when the cation approached this anion, this cation attracted its electron cloud towards itself, due to which distortion of electron cloud took place over here. right? This electron cloud, it was spherical in the beginning. Now, electron density has shifted in this particular direction. If electron density has shifted in this particular direction, can I say it is similar if I say something like this? Can I say we can interpret it like this? Since electron density has shifted in this particular direction, can I say this electron density is now somewhat mutually shared by cation and anion? Can I say this electron density somewhat is now mutually shared between cation and anion? Right? And mutual sharing, that happens in covalent, right? That happens in covalent bonds, right? So in the beginning, I took cation and anion. They were supposed to form the ionic bonds. They were supposed to form the ionic bond. Perfect. But at the same time, the distortion of electron cloud of anion took place. Electron density of anion shifted towards the cation. Now, as if this electron density which got shifted towards cation, somewhat we can say this electron density is now being shared between cation and anion. So in short, can I say, since now there is mutual sharing of this electron cloud, can I say somewhat covalent character got generated, covalent character got established in the ionic bond here? Yeah? Right, people? That is something which was this particular statement all about. Due to polarization, covalent character is induced in what? Covalent character is induced in an ionic bond. And my dear students, covalent character in an ionic bond, that is directly proportional to polarization. More the polarization, more the distortion of electron cloud of anion. That means more electron density will shift towards the cation. That means more will be the sharing of electron density between cation and anion. That means more will be the covalent character. Yeah? Is it clear? Is this point clear to everyone? Quickly say yes or no in the chats. So due to polarization, what happens? Covalent character is induced in an ionic bond. And more the polarization, more the covalent character in an ionic bond. So I can generalize a statement over here. Covalent character in an ionic bond, that is directly proportional to what? Polarization. Okay? Now the point is, on what factors this polarization depends upon? On what factors this polarization depends upon? My dear students, polarization, distortion of electron cloud, right? Polarization, that depends on the first factor is your polarizing power of cation. Polarizing power of cation, which is also called as ionic potential of cation. This is also called as ionic potential of cation. Either you call it as polarizing power of cation or you call it as the ionic potential of the cation. Now, this is the first factor on which what? On which your polarization depends upon. That is polarizing power of cation. Now, how do we define this polarizing power of cation? How do we define it? Let me first of all tell you. Polarizing power, it is defined for what? This term is defined for the cation. This term, polarizing power, it is defined for cation. And what it's all about, what it means? It means that polarizing power of a cation, it is basically the tendency of the cation to distort electron density of the anion. The tendency of the cation to attract the electron density of anion towards itself. The tendency of the cation to distort the electron cloud of anion towards itself. What do we call that as? We call that as polarizing power of cation. Right? So what is polarizing power? It is basically the tendency of what? Tendency of the cation to distort the electron cloud of anion, to attract the electron cloud of anion towards itself. Now, my dear students, tell me just one thing. More the polarizing power of cation, I would say more will be the tendency of the cation, to attract the electron density of anion towards itself. Due to which, more will be the polarization. If more is the polarization, That means more electron density is shared between cation and anion. Hence, more will be the covalent character. Now, can you relate covalent character with the polarizing power of cation? Absolutely. I'll say covalent character in an ionic bond is directly proportional to polarizing power of cation. More the polarizing power of cation, more is going to be the covalent character in short. Simple. Yeah. Now, the point is, on what factors this polarizing power of cation depends upon? It depends upon generally two factors. Polarizing power of cation depends on two factors. It depends on the charge on cation and it depends on the size of cation. More the charge, more the positive charge on cation, more the positive charge on the cation, more is its tendency to distort the electron cloud of anion. Simple. More the positive charge on cation, right? More is going to be its tendency to distort the electron cloud of anion, right? More is going to be its attractive power. Perfect. More electron density will be shared between cation and anion. Hence, more is the covalent character, in short. Yeah. Similarly, size. Lesser the size of cation, more is going to be its positive electron density. You did not understand what I said. I said lesser the size of the cation, more is going to be its positive volume charge density. Just understand what I'm trying to say. Lesser the size of cation, more is going to be its positive volume charge density. And more the positive volume charge density, more will be the distortion of electron cloud. More the distortion of electron cloud, more will be the polarization. More the polarization, more is going to be the covalent character, in short, right? So as the size of cation decreases, positive charge density of the cation increases. Okay? Right? I'm writing this particular statement over here. So remember it from now onwards. I'm writing it over here. Lesser the size of the cation, more is going to be its positive charge density. Hence, more distortion will happen. More distortion of electron cloud of anion is happen. Hence, more the polarization. And we know, more the polarization, more the covalent character. So in short, you just have to remember this statement. Covalent character in an ionic bond. It is directly proportional to polarizing power of cation. Polarizing power of cation is directly proportional to charge on cation, inversely proportional to size of cation. That's all. Nothing else. Okay? Perfect. Now guys, since I told you polarizing power of cation is directly proportional to charge, inversely proportional to size. Now you are going to let me know the answers of these questions. Among these two cations, which one has got more polarizing power? Among these two? More the charge of the cation, more the polarizing power. More the charge of the cation, more the polarizing power. More the charge of the cation, more the polarizing power. Is this the order? Yeah? Is this the order? Siddharth, you can drag the video a little back. You can repeat it. You can watch it. There's a live session going on. Okay, just drag the video a little back. Perfect. And it's better to join the class earlier than to say, please reteach. Perfect. I believe this is clear. Now tell me one thing. Among these cations, which one has got more polarizing power? Which one has got more polarizing power? First of all, the charge on each cation is same. The magnitude of charge is same. If the magnitude of charge is same, then you'll be deciding on the basis of size. You know, polarizing power of cation is inversely proportional to size. Lesser the size of cation, more will be the polarizing power of cation. So which cation is lesser in size? Lithium, sodium, potassium, rubidium, cesium. Down the group, size increases. So which one has got lesser size? Li positive. If Li positive has got lesser size, it will be having more polarizing power. Right? Similarly, beryllium, magnesium, calcium, strontium, barium. Beryllium, magnesium, calcium, strontium. Group second elements. Down the group, size increases. So which one has got least ionic size? B di positive. Lesser the size, more the polarizing power. So which one has got more polarizing power? This is the order of the polarizing power of the cations. Right? Perfect. As I told you, polarizing power of cation, this is also called as what? You call it as the ionic potential as well. Okay? And my dear students, remember one more simple thing. Remember one more thing. This will be helpful in a lot of questions. Polarizing power of cation also depends upon the effective nuclear charge when it comes to the d block elements. In case of your d block elements, polarizing power of cation depends on the effective nuclear charge as well. And remember, in short, polarizing power of cation is directly proportional to effective nuclear charge of your cations. Why is that? Because more the effective nuclear charge, more the attractive power. If the effective nuclear charge of cation is more, its attractive power will be more. If its attractive power will be more, it will be attracting more electron density of anion towards itself, due to which more electron density will be shared between cation and anion. Hence, more the polarization. If more is the polarization, more is going to be the covalent character. Simple. Right? Simple. So, polarizing power of cation also depends on the effective nuclear charge of the cations as well, particularly when it comes to the d block elements. Right? And in case of d block elements, one simple thing I'm going to tell you. One simple thing. For example, you would have studied the 3D series, right? 3D series. Generally, on moving from left to right. In the, for example, 3D series. On moving from left to right. What happens to effective nuclear charge in case of d block elements? Remember it increases, right? For example, you are moving from 3D to 4D, then 4D to 5D. What happens down the group? Again, the effective nuclear charge here in case of d block elements, it generally increases. I'm using the term generally. Left to right, generally, effective nuclear charge increases. Top to bottom, in case of from 3D to 4D, 4D to 5D, generally, effective nuclear charge increases. Okay? Now, why am I telling you all this? Because you need to compare the polarizing power of these cations over here. Fe di positive, cobalt di positive, nickel di positive, copper di positive. On moving from left to right, in the d block elements, effective nuclear charge increases. If effective nuclear charge increases, polarizing power of the cations will increase. Right? Perfect? Simple. Simple, guys. Perfect? This statement already I told you. From top to bottom, from 3D to 4D, 4D to 5D, effective nuclear charge again, effective nuclear charge increases. And if effective nuclear charge increases, polarizing power, attractive power increases, polarizing power increases. Right? Now, can you tell me the order of polarizing power in case of zinc di positive, cadmium di positive, mercury di positive? Tell me quickly. Quickly, my dear students. Zinc is your 3D element. This is your 4D element. This is your 5D element. Right? They're from the same group. 3D, 4D, 5D. I told you a few minutes back only. What happens to effective nuclear charge? From 3D to 4D, 4D to 5D. It increases, hence polarizing power increases. So polarizing power of Hg di positive will be maximum among all these three. Right? So my dear students, I hope you got to know the first factor on which polarization depends upon. That is polarizing power of the cation, which is also called as ionic potential. And this polarizing power depends on is directly proportional to charge on cation, inversely proportional to size of cation. Right? Perfect. And in case of d block elements, remember from now onwards, polarizing power of cation is directly proportional to effective nuclear charge of cation. Right? On moving from left to right, generally in case of d block elements, your Z effective increases. And again, from 3D to 4D, 4D to 5D, Z effective also increases. Okay? Now, the second factor on which polarization depends upon, that is polarizability. Polarizability is defined for anions. Polarizing power was defined for cations. Polarizability is defined for what? It is defined for Polarizability is defined for anions. What is polarizability of an anion? Simple. The tendency of the anion, the tendency of an anion to get polarized. The tendency of an anion to get polarized. So I can simply say, more the polarizability of an anion, more the polarizability of an anion, more will be the tendency of the anion to distort its electron cloud. To distort its electron cloud. More will be the distortion of its electron cloud. More electron cloud of the anion will get shifted towards cation. Hence, at the end, more will be the polarization. And if more the polarization, and if more is the polarization, more will be the covalent character. I believe I'm clear. I believe I'm clear. Yeah? So remember this polarizability. It is defined for anions. And it is basically the tendency of an anion to distort its electron cloud. Right? More the tendency of the anion to distort its electron cloud, more will be the distortion. More the distortion means more electron cloud will be shifted towards the cation. And if more electron cloud of anion gets shifted towards the cation, more will be the polarization. If more is the polarization, more is going to be the covalent character. Simple. Right? So remember from now onwards, polarizability of an anion. I'll write it over here. Polarizability of an anion. Polarizability of an anion is also directly proportional to what? Polarization. More the polarizability of an anion, that means more is its tendency to distort its electron cloud. Hence, more the polarization. If more is the polarization, I would directly say more is the covalent character. So, covalent character in case of ionic bond is directly proportional to what? Is directly proportional to polarization of anion as well. Now, this polarization of anion, this polarizability of anion is directly proportional to charge on anion, which is basically the negative charge on anion, and is also directly proportional to size of anion. Okay? So remember, polarizability of anion is directly proportional to charge on anion and also is directly proportional to size of anion. Also is directly proportional to size of anion. Okay? Perfect. Sir, please teach us coordinate covalent bond. I will teach everything. Just wait. Just focus on this. Why you are continuously spamming in the chats? I fail to understand. I believe this particular point is clear to everyone. Okay? So guys, it's evident. More the size of the anion. If the anion is bigger sized, the nucleus of the anion cannot hold its electron density firmly towards it. The nucleus of the anion cannot hold its electron density firmly towards it. So this electron cloud can easily get distorted when cation approach towards it. It can easily get distorted. And if the electron cloud easily gets distorted, you can clearly say its polarizability is more. Its tendency to get polarized is more. It has got more tendency to distort its electron cloud. Simple. So remember this particular statement, it's super important. Now, I believe this particular point is clear. More the charge on anion. I told you, polarizability of anion depends on two factors. One is size of anion, one is charge on anion. More the charge on anion, lesser is going to be its effective nuclear charge, right? Okay? Lesser is going to be effective nuclear charge. If lesser is the effective nuclear charge of anion, guys, look at this particular statement properly. Look at this particular statement properly. More the charge on anion, lesser is going to be the effective nuclear charge of anion. If lesser is the effective nuclear charge of anion, that means the anion, the nucleus of anion, will not firmly hold its electron cloud. That means its electron cloud can easily get distorted. That means its polarizability is more. Right? Perfect. As simple as that. Now, where do I use all this? N trinegative, O dinegative, F negative. Where is the polarizability more? Which anion can easily get polarized? Polarizability of an anion is directly proportional to charge on anion. More the charge on anion, more is the polarizability. That means more is the polarizability of the anion. So more is the tendency of the anion to distort its electron cloud. More distortion means more polarization. More polarization means more covalent character. Simple. Yeah? Okay, what about the answer of this question? P trinegative, S dinegative, Cl negative. Which anion can easily get distorted? Which anion has got more polarizability? More the charge on anion, more is the polarizability of anion. Okay? Right? This is something I told you. Polarizability of anion is directly proportional to size of anion. Directly proportional to charge, directly proportional to size. Right? Perfect. Now you can answer these questions for sure. F negative, Cl negative, Br negative, I negative. Arrange them on the basis of their polarizability. Arrange them on the basis of their polarizability. Chlorine, chlorine, bromine, iodine. Down the group size increases. So more the size of the anion, more the polarizability. Right? Oxygen, sulfur. Oxygen, sulfur. Down the group size increases. More the size, more the polarizability. N trinegative, P trinegative. N trinegative, P trinegative. Down the group size increases. More the size of anion, more the polarizability of anion. Simple. Correct? Correct, people? I believe I'm clear till here. Now, let's summarize all of this and let's exactly see what kind of questions are asked when it comes to the Fajan's rules. So first of all, covalent character. Covalent character. Let me write it over here. Covalent character in an ionic bond. First of all, that is directly proportional to polarization. That's directly proportional to polarization. That's directly proportional to distortion of electron cloud. Number one. Number two, polarization is directly proportional to what? It is directly proportional to polarizing power of cation. Again, polarization is directly proportional to polarizability of an ion. It is directly proportional to polarizability of an ion. Right? Perfect. At the same time, polarizing power of cation is directly proportional to charge on cation and inversely proportional to size of cation. Simple. Polarizability of an anion is directly proportional to charge on anion, directly proportional to size of anion. Right? And you know, your covalent character itself, it will be inversely proportional to ionic character. More the covalent character means lesser the ionic character. Lesser the covalent character means more the ionic character. Yeah? Perfect? I believe I'm clear. So remember these things and you're done, you're sorted. You can easily solve all the types of questions which are asked when it comes to your Fajan's rules. See guys. Arrange the following on the basis of their covalent character. Arrange the following on the basis of their covalent character. Now, first of all, this is ZnCl2, cadmium Cl2, HgCl2. So, first of all, this is zinc di positive here, Cl minus 1. How did I get plus 2 minus 1? Just crisscross. I told you this in redox. This is plus 2, this is minus 1. Similarly, this is plus 2, this will be minus 1. Similarly, this will be plus 2, this is minus 1. First of all, anion everywhere is same. So I cannot decide on the basis of anion. Leave anion aside. Leave anion aside. Talk in terms of cation. The charge on every cation is same. The charge on every cation is same. But leave the charge part also aside. This is zinc di positive, cadmium di positive, Hd di positive. This is 3D element, this is 4D, this is 5D. 3D to 4D, 4D to 5D. Z effective increases. If Z effective increases, polarizing power of cation increases. If polarizing power of cation increases, that means covalent character increases. So which one will be having more covalent character? This is odd. Simple. Right? Over here, anion everywhere is same. Leave that aside. Talk in terms of cation. Talk in terms of cation. Right? 3D, 4D, 5D. 3D, 4D, 5D. What happens? Z effective increases. Z effective increase means polarizing power of cation increases. Right? And if polarizing power of cation, that is directly proportional to covalent character. So where do you see more covalent character? This is the order. See, in this particular case, again, anion everywhere is same. So talk in terms of cation. Li positive, this positive, this positive, this positive. See, we have to discuss on the basis of the cations. First of all, if you look carefully, charge on every cation is same. Talk in terms of size. Charge on every cation is same, right? So don't decide on the basis of charge. Decide on the basis of size, right? Li positive, Na positive, K positive, Rb positive, Cs positive. So lithium, sodium, potassium, rubidium, cesium. On moving down the group, size increases. So which cation is smaller in size? Li positive. Which cation is smaller in size? Li positive. Smaller the size of cation, more the polarizing power of cation. More the polarizing power of cation, more is the covalent character, because covalent character is directly proportional to polarization. Polarization is directly proportional to polarizing power of cation, and that polarizing power of cation is directly proportional to what? Sorry, that is inversely proportional to size of cation. So this is the order of your covalent character. This is not BCl2, this is BeCl2, okay? Okay, understand. So in this particular question, your cation everywhere is same. So leave your cation aside. Talk in terms of anions now. Talk in terms of anions. This is F minus 1, Cl minus 1, bromine minus 1, iodine minus 1, right? Talk in terms of anions. For anions, what do we define? Polarizability, right? See, the charge on every anion is same. So decide on the basis of size. More the size of anion, more will be its polarizability. More the polarizability of anion, more is the polarization. More the polarization, more the covalent character. Done and dusted, right? So, which anion has got maximum size? I negative has got maximum size, right? Simple. Perfect. So you can remember it like this also now. Smaller the cation, larger the anion. Smaller the cation, larger the anion. More will the covalent character. Right? Covalent character is favored by smaller cation and larger anion. Covalent character is favored by smaller cation and larger anion. Tell me the answer of this question now. First of all, cation everywhere is same. So cut it out. This is F negative, Cl negative, Br negative, I negative. Charge on every anion is same. Talk in terms of size. More the size of anion, more the size of anion, more the covalent character. In short. If this is the order of the covalent character, if I ask you what will be the order of ionic character, reverse of it. Just reverse this order. That gives you the ionic character order. Simple. Okay. Look at this particular question. Cation everywhere is same. Talk in terms of anion. F negative, Cl negative, Br negative, I negative. Charge on every anion is same. Talk in terms of size. More the size of anion, right? More is the covalent character, right? Same goes for this and same goes for this. I believe all these questions are perfectly clear to you. Now guys, one more important statement. One more important statement. This is again very important. Polarizing power of that cation, which has got pseudo inert gas configuration. Remember this. Polarizing power of that cation, which has got pseudo inert gas configuration, is always greater than the polarizing power of the cation, which has got inert gas configuration. Now, first of all, what is pseudo inert gas configuration? Whenever you see any cation whose electronic configuration resembles like this, first you write inert gas configuration followed by D10. What does that mean? For example, you have got copper. What is the outermost configuration of copper? What is the outermost configuration of copper? It is 3D10, 4s1, right? It is 3D10, 4s1. Perfect. It is 3D10, 4s1. And before this 3D10, you'll be writing what? Inert gas configuration, right? So can you let me know in the chats, before 3D, which inert gas should I write? Argon, xenon, what? What exactly? What exactly? Recently you are done with the periodic classification. Can you let me know in the chats? Quickly. Quickly, guys. Quickly. You should know it. It's argon, right? So I'll write first argon, followed by 3d10, 3s1. This is the electronic configuration of copper, right? My dear students, if I take one electron out of it, it becomes copper positive. Now its configuration will be argon, followed by 3d10 configuration, and 4s is 0. Look at this particular configuration. Look at the configuration, outermost configuration of what? Of your argon. It is noble gas configuration, followed by D10 configuration. Noble gas configuration, followed by D10 configuration. This is something which we call as pseudo inert gas configuration. And cation, which has got pseudo inert gas configuration, has got more polarizing power than that particular cation which has got exactly inert gas configuration. For example, let's say you have got sodium. What is the configuration of sodium? Can you let me know in the chats quickly? Sodium, 3s1 outermost configuration, right? Outermost configuration is 3s1 in case of sodium. So I'll be writing neon followed by 3s1, right? If I take one electron out from sodium, it becomes Na positive. Now it is just neon. So Na positive has got same configuration as that of the noble gas neon. Perfect. So this configuration, Na positive has got inert gas configuration. Na positive has got inert gas configuration. This Cu positive has got pseudo inert gas configuration. That cation which has got pseudo inert gas configuration, its polarizing power will be always more than that of that cation which has got inert gas configuration. This is also one important point which is used in the questions. For example, among these two, can you tell me which one has got more covalent character? CuCl or NaCl? See, this is Cu positive, Cl negative. Na positive, Cl negative. So, if you want to compare the covalent character, you cannot discuss it on the basis of the anion because anion is same. Anion is same in both the cases. Now, talk in terms of cation. Cu positive. Few minutes back only I told you this has got pseudo inert gas configuration, right? And this has got exactly the inert gas configuration. That cation which has got pseudo inert gas configuration, its polarizing power is more. And more the polarizing power, more is going to be the polarization, more is going to be the covalent character. Which one has got more covalent character? CuCl has got more covalent character, right, than that of your NaCl. Perfect. Now, my dear students, what different types of questions can be asked from Fajan's rules? Understand and remember. And nothing apart from all these things will be asked in your examination. Trust me on that. Okay. Look at this particular concept. This is the application of Fajan's rule. My dear students, Ag2S is less soluble than Ag2O. Because covalent character of Ag2S is greater than that of Ag2O. What does it mean? We are talking about solubility. One simple thing I'm going to tell you. Solubility. When you talk about the solubility of ionic compounds will be greater than that of solubility of covalent compounds when solvent is polar in nature. Solubility of ionic compound, generally, what you'll observe it is greater than that of covalent compounds when you have got polar solvent. Solvent here, I'm taking polar, right? Why is that? Because like dissolves like. Ionic means it will get dissolved more in polar. Perfect? Right? Or in short, you can say like this. Solubility is directly proportional to ionic character, inversely proportional to covalent character, if the solvent is polar in nature. Now talk about Ag2S and Ag2O. Whose solubility will be more, for example, in water? Whose solubility will be more? First of all, my dear students, over here you have got Ag positive, S dinegative, Ag positive, O dinegative. So, first of all, the cation is same everywhere. Leave it. Talk in terms of anion. Charge on anion is same. Talk in terms of size of anion. Size of S dinegative is more than that of O dinegative. Oxygen, sulfur, down the group size increases. Size of this anion is more. So, more polarizability, more covalent character. It has got more covalent character. If this is the order of covalent character, tell me the order of ionic character. Ionic character order will be reverse of it. This is the order of ionic character. And more the ionic character, more the solubility. So I would say Ag2O, its solubility, Ag2O, its solubility will be more than that of what? Ag2S. This is the order of solubility. That's what I mentioned over here. Ag2S is less soluble. Ag2S is less soluble than Ag2O, right? Which is explained by the Fajan's rules. Simple. Number one. Number two. Look at this particular statement. We have got FeOH whole thrice. We have got FeOH whole thrice and FeOH whole twice. FeOH whole twice. Over here, you have got Fe tripositive, OH negative. Fe dipositive, OH negative. Compare their covalent characters. First of all, you cannot decide on the basis of anion because it's same. So talk in terms of cation. The charge on cation here is more. More the charge on cation, more the polarizing power of cation, more the covalent character. So this is the order of covalent character. Tell me the order of ionic character. Ionic character order will be this. This will be the order of ionic character. Right? This will be the order of ionic character. Perfect. And if this is more ionic character is directly proportional to solubility here. Right? So what about solubility? I would say FeOH whole twice will be more soluble than that of FeOH whole thrice. That's what would be mentioned here also. FeOH whole thrice is less soluble. It is less soluble than FeOH whole twice, which is explained by Fajan's rule. I hope you're understanding. Right? I hope you're understanding the logics which I'm giving you. Now guys, one more thing. Questions can be asked on melting point as well. And remember one thing. Generally, you'll observe one thing. Melting point of ionic compounds will be greater than that of covalent compounds. Melting point of ionic compounds will be greater than that of the covalent compounds. Or I can say something like this. Melting point of ionic compounds is more than that of covalent compounds. Or I can say melting point is directly proportional to ionic character. So if it is directly proportional to ionic character, that automatically tells you it's inversely proportional to covalent character. So you can solve the questions based on this particular statement as well. For example, understand guys. Let's say I've got BeCl2, beryllium, magnesium, calcium, strontium, barium. Right? These are the chlorides of group second. I need to arrange them on the basis of their melting point. So again, I'll be using Fajan's rule. See, this is Be dipositive, Mg dipositive, calcium dipositive, strontium dipositive, barium dipositive, right? I won't be deciding on the basis of anion. Leave anion aside, right? Talk in terms of cations. Charge on every cation is same. So don't decide on the basis of charge of cation. Decide on the basis of size of cation. Lesser the size of cation, more the covalent character. So what is the order of covalent character? BeCl2 will be maximum covalent, followed by MgCl2, and at the end, what do I write? At the end, I'll be writing BaCl2. This is the covalent character order. So if this is the covalent character order, what will be the ionic character order? Opposite of it. So BeCl2, then all the others, and at the end, BaCl2. This is the ionic character order. And we know more the ionic character, more the melting point. So I would say BaCl2, its melting point will be maximum, right? So what will be the order of the melting point? Melting point will follow the same order. BeCl2, MgCl2, CaCl2, strontium chloride, followed by BaCl2. This is the melting point order, right? Perfect. This is the melting point order. Got it? This sort of a question can be asked as well. One more question can be asked that is based on thermal stability. That's based on which one is thermally, you would have seen those sort of questions, which one is thermally more stable. Again, Fajan's rule is going to help us in that. How exactly? Understand. Remember again, thermal stability of ionic compounds. Thermal stability of ionic compounds will be greater than that of thermal stability of covalent compounds. Ionic compounds have got more thermal stability than covalent compounds. Or I can say something like this. Thermal stability is directly proportional to ionic character, inversely proportional to covalent character. Simple. Simple. Now, for example, this is the question. You have got lithium carbonate, you have got sodium carbonate, you have got potassium carbonate, lithium, sodium, potassium, you have got rubidium carbonate, you have got cesium carbonate. These are the carbonates of group first elements. These are the carbonates of group first elements. Understand? Tell me, which one is thermally more stable? Talk in terms of Fajan's rules. See, anion everywhere is same. Leave it. Talk in terms of cation. Li positive, Na positive, K positive, Rb positive, cesium positive. Charge on cation everywhere same. Leave it. Talk in terms of size of cation. Lesser the size of cation, more the covalent character. So, I would say Li2CO3 will have more covalent character than that of Na2CO3, then that of K2CO3, then that of Rb2CO3, then that of CS2CO3. This is the order of the covalent character, right? Reverse of it will be the order of ionic character. Perfect. And you know, more the ionic character, more the thermal stability. So I would say thermal stability order will follow like this. This is the order of your thermal stability. I hope you can easily solve the questions based on solubility. You can easily solve the questions based on melting point. You can easily solve the questions based on thermal stability with the help of Fajan's rules. If I'm clear, let me know once in the chats quickly with some fire emojis. Yeah? Quick, people. After this lecture, it's going to take one more lecture, as I told you, right? And part 3 of this particular chapter will happen on Tuesday. Tuesday, 7 p.m. We'll complete this chapter on Tuesday. Okay? Perfect. Perfect, guys. So this was your Fajan's rules. I believe it is perfectly super clear to all of you. Now comes one more important point, which you study mainly in your organic chemistry. That is dipole moment. That is dipole moment, right? This is again one important question, guys, right? And a lot of variation is there in the dipole moment. I'll show you a lot of questions, but before showing you the questions, let me tell you what this dipole moment exactly is all about. See, guys, what this dipole moment exactly is all about. First of all, understand like this. Let's say you have got two charges plus Q and minus Q. Let's say you have got two charges plus Q and minus Q, separated by certain distance A. Separated by certain distance A. Whenever you have got opposite charges, whenever you have got charges separated by certain distance, whenever you have got charges separated by certain distance, let me tell you, this system of charges, the system of charges separated by certain distance, this system of charges is something which you call as, dipole. System of charges separated by certain distance is what you call as dipole. Just a second, guys. Just a second. Okay. So what I was trying to say is, the system of charges which are separated by certain distance, the system of charges is something which we call as dipole. And for the dipole, we define a term. What is that? Dipole moment, represented by mu. For the dipole, we define a term, dipole moment, represented by mu. What is dipole moment? It is basically charge multiplied by distance. Charge multiplied by distance gives me the dipole moment here. Okay? This dipole moment, it is a vector quantity. This dipole moment is a vector quantity, right? units of the dipole moment are going to be d by SI unit of dipole moment. Okay. Since dipole moment is a vector quantity, its direction in chemistry is taken either from positive to negative, or in chemistry I can say less electronegative element to more electronegative element. Less electronegative element to more electronegative. First of all, whenever you'll be having a system of charges separated by certain distance, the system of charges separated by certain distance is what you call as dipole. For the dipole, we calculate its moment, right? Dipole moment, which is defined as the product of charge and the distance. Dipole moment, it's a vector quantity, right? It has got the units as d by. Since it's a vector quantity, so it will be having the direction. Its direction is either from positive to negative, or you can say from less electronegative element to more electronegative element, in short, right? Now, for example, I've got a molecule HCl. Tell me one thing. Which one among hydrogen and chlorine is more electronegative? I would say chlorine is more electronegative. So this electron pair will be shifted towards chlorine. Chlorine will be getting delta negative. Hydrogen will be getting delta positive. Right? Delta positive, delta negative. Tell me one thing. Do we have equal and opposite charges separated by certain distance? Yes, we have equal and opposite charges separated by certain distance. Yes, we have equal and opposite charges separated by certain distance. What do you call this as? Can I say this is same like your dipole? If it behaves like your dipole, it will be having the dipole moment, right? And the direction of dipole moment is from less electronegative to more electronegative. This is the direction of the dipole moment. Okay? Am I clear? Am I clear, people? This is the direction of dipole moment. Yeah? Now, few more points. Let me tell you, lone pair also contributes. Towards the dipole moment. Lone pair also contributes towards the dipole moment. And let me tell you, the direction of dipole moment due to lone pair is, if I talk about the direction of dipole moment due to lone pair, is towards the lone pair. What does that mean? That means, for example, you have got atom A. Let's say you have got atom A. This atom A has got a lone pair here, right? Lone pair will be also contributing towards dipole moment, and its direction, the direction of dipole moment due to lone pair is towards the lone pair. Towards the lone pair means, that means the direction will be in this way, due to the lone pair. Right? Right, people? Yeah? Now, understand one more thing, and do remember it. You'll be using it frequently everywhere. My dear students, that molecule whose net dipole moment is 0, you call that molecule as a non-polar molecule. You call that as the non-polar molecule. And that molecule whose net dipole moment is non-zero, you call that as the polar molecule. You call that as the polar molecule. Okay, you call that as the polar molecule. For example, I'm taking BeCl2. Let's say I've got BeCl2. I believe you would be knowing its structure. This is B, this is chlorine, and this is chlorine. This is your BeCl2. Now, my dear students, tell me just one thing. If you talk about this particular bond, chlorine, beryllium, more electronegatives, chlorine. So delta negative, delta positive. Talk about this particular bond, chlorine more electronegative. So delta negative, delta positive. So my dear students, how many bond moments do you got over here? You got 2 bond moments. One will be from positive to negative in this direction. One will be in this particular direction. So equal and opposite bond moments, they'll cancel out. So if I ask you, what is the net dipole moment here? net dipole moment here is 0. So should I be calling this particular molecule as polar or non-polar? It is the example of the non-polar molecule, right? For example, you have got carbon dioxide. You have got carbon dioxide. I believe you know its structure. I believe you know its structure. This is your carbon, double bond O, double bond oxygen. Now, talk about this particular bond first between carbon and oxygen. Which one is more electronegative? Oxygen. So delta negative, delta positive. Similarly, delta negative, delta positive. So how many bond moments you got over here? The first bond moment, the second bond moment. From positive to negative. Similarly, from positive to negative. Equal and opposite bond moments, right? They'll cancel out. So net dipole moment here is 0. If net dipole moment of the molecule is 0, so this particular molecule overall is non-polar. Molecule overall is non-polar. No doubt. Bonds are polar. Bonds are polar. Bonds are polar here. But the overall molecule is non-polar. Similarly, the bonds are polar here. The bonds are polar. But overall molecule is non-polar. Correct? Tell me one thing. HF. Is it polar or non-polar? Polar or non-polar? Delta negative, delta positive. This direction. So its net dipole moment is non-zero. So it's a polar molecule. It's a polar molecule. Now, my dear students, right now I'm going to give you a set of molecules. Just remember it. When I'll be teaching you VSCPR, there I'll be explaining you all those things. But right now I would want you guys to take a note. Right now I would want you guys to take a note of certain things. Whenever you see a molecule of the type AB2L0, AB3L0, AB4L0, AB5L0, AB6L0, AB2L3, AB2L3 and AB4L2, AB4L2. Whenever you see molecules of these types, whenever you see molecules of these types, remember directly their net dipole moments are going to be 0. These molecules are going to be non-polar. Now you must be thinking, what is this AB2L0, AB3L0? This is something which I'll be discussing with you when I'll be teaching you VSEPR. But right now, just take a note. Since we are learning dipole moments, so you need to write it in the notes right now itself. Okay? So that your notes will be complete related to dipole moment. Perfect? What is meant by these molecules, you'll get the idea when I'll be teaching you VSCPR. Right? Am I clear till here? Am I clear till here? Now guys, if all this stuff is clear, then it's high time to solve the questions. Start with the third question. Start with the third question. HF, HCl, HBr, HI. In short, your dipole moment is equal to Q multiplied by A, right? So can I say more the electronegativity difference, between the atoms? If more the electronegativity difference between the atoms, then more will be the charges on the atoms. More the charges on the atoms, more will be the dipole moment, right? So generally, this is going to be the major rule which you are going to remember. More electronegativity difference means more dipole moment. It has got some exceptions as well, which I'll tell you in some time. But right now, in majority of the cases, you'll follow this particular thing. More the electronegativity difference, more is going to be the dipole moment. So, solve the last one. HF, HCl, HBr, HI. Where is the electronegativity difference more? In this one, HF. Electronegativity difference is more here. More the electronegativity difference, more the dipole moment. This is the order. Done. Look at the second question. CH. So let's not talk about CH over here. Let's talk in terms of CCl. Now this is C and Cl. Which one is more electronegative? Chlorine. So delta negative, delta positive. Right? Similarly, this will be delta negative, delta positive. Right? So what will be the moment due to this particular bond? Positive to negative. Positive to negative. So both the vectors are going in one direction. So resultant is going to be in this direction. Resultant of net dipole moment will be in this direction. Right? Look at this one. This is positive. This will be negative. Right? Positive and negative. So positive to negative, positive to negative. equal and oppositely, equal and opposite moments. Equal and opposite moments. So net will be 0. Here net dipole moment is 0. Here net dipole moment is something. So compare the dipole moments. A greater than B. A greater than B. As simple as that. NH3 and NF3 I'm going to show you separately. NH3 and NF3 I'll show you separately. This is NH3 for example, and this is your NF3 for example. NH3, NF3. My dear students, if you talk about NH3, this is how your NH3 looks like. If you talk about NF3, this is how your NF3 looks like. Right? One is NH3, one is NF3. Now try to understand. Try to understand few things. Nitrogen, hydrogen. Less electronegative, more electronegative. So bond moment here will be from less to more. Less electronegative to more electronegative. Less electronegative to more electronegative. Lone pair also contributes towards the dipole moment. Its direction is towards the lone pair. So do you see all these bond moments converging in one direction? So net dipole moment will be in this direction. This is your net dipole moment here for this particular molecule. Now talk about this. Less electronegative to more electronegative. Less to more. Less to more. Towards the lone pair. My dear students, in this particular scenario and in this particular scenario, you have got 4 vectors over here. Right? Here also you have got 4 vectors. But one vector is pointing upwards. All the others are pointing downwards. So can I say in this particular case, there will be some cancellation of vectors? Right? If there is some cancellation of vectors here, so can I say net dipole moment of NH3 will be more than that of the NF3? Because in NH3, is there any cancellation? No. Here cancellation is there. Right? I believe these sort of questions you can easily solve from now on. Okay? Give me the order of the dipole moments here. Give me the order of the dipole moments here. Give me the order of the dipole moments here. Quick. You're supposed to be quick. Give me the order of the dipole moments here. See guys, CH3, is it donating, electron donating or withdrawing? This is something which I believe you guys know. CH3, it is electron donating. It's electron donating. NO2 is electron withdrawing. Is electron withdrawing. NO2 is withdrawing, CH3 is donating. Okay. Now, look at this particular case. If CH3 is electron donating, it donates electrons. When it donates electrons, can I say it gets delta positive and this gets delta negative? When it donates electrons, delta positive, delta negative. So bond moment positive to negative, bond moment positive to negative, right? Equal and opposite bond moments. So net here will be 0. Net here will be 0. Look at this particular case. This is positive, this is positive, negative, positive to negative. So 2 vectors, one pointing downwards and one pointing in this direction, right? At an angle of what? At an angle of 120 degree. So 2 bond moments at the angle of 120. Positive to negative, positive to negative. One pointing downwards, one pointing in this direction. At an angle of what? At an angle of 60. These are basically vectors, right? Perfect. And one thing which I believe you guys know, lesser the angle between the vectors, more will be the resultant, right? Yeah. Lesser the angle between the vectors, more is going to be the magnitude of the resultant. So where will be the magnitude of resultant more? Here it is already 0. Here the angle is 120. Here the angle is 60. So C will give more resultant followed by B followed by A. Simple. Right? Look at the next case. CH3 is donating. So when it donates electrons, delta positive, delta negative. This NO2 is withdrawing. When it withdraws electrons, delta negative, delta positive. So give me the direction now. Positive to negative here. Positive to negative. Positive to negative here also. Positive to negative here also. So one moment is pointing downwards, one moment is pointing in this direction. Right? Shifting of vectors, I believe you would have studied. What is the angle between these two vectors here? It is 120 degree. Right? Now, positive, negative. Downwards, right? Positive to negative. In this direction, one vector is going downwards, one vector is going in this direction. The angle here is 60, right? Positive to negative. Positive to negative. Both the vectors are going downwards. Angle here is 0. Angle here is 0. Now, lesser the angle between the two vectors, more is going to be the magnitude of the resultant. So, where will the resultant more? In C. So, net dipole moment of C is more, followed by B, followed by A. Done and dusted. Right? Is it clear? Is it clear? Now, guys, leave this case aside. Talk about all the other cases first of all. H2O and H3. Here the bond is between O and H. Here the bond is between N and H. N and H. More the electronegativity difference, more the electronegativity difference, more is going to be the dipole moment, which I told you a few minutes back. This is the order. More the electronegativity difference, more the electronegativity difference, more is going to be the dipole moment. Simple. Yeah? Look at the first case. This remember separately. See, my dear students, till now we were basically comparing the dipole moments. Since dipole moment is basically Q multiplied by A. And I told you more the electronegativity difference between the atoms, more the charges on the atoms, more the charge, more the dipole moment. Something which I told you a few minutes back. So till now, we were comparing the dipole moments on the basis of charge. And we used to ignore this parameter, A. What is A? Distance between the atoms. So basically, you cannot ignore A all the time. You cannot ignore A all the time. Dipole moment, it depends on two factors, two things. One is charge, one is distance between the atoms, right? This charge, it depends on what? Electronegativity difference. More the electronegativity difference, more the charges, more the dipole moment. More the value of A, more the dipole moment, right? So dipole moment basically depends on two factors, charge as well as the distance. Now understand. Here you have got a bond between carbon and fluorine, carbon chlorine, carbon bromine, carbon iodine, right? As per the charge factor is concerned, what should be the order of dipole moment? More the electronegativity difference, more the dipole moment, right? So basically, as per charge factor, this has to be the order 1, 2, 3, and 4. This has to be the order of the dipole moment as per the charge factor, right? Now, as per distance factor, PCl bond length is more than that of CF bond length. If CCl bond length is more, distance is more here. If distance is more here, its dipole moment should be more. So 2, as per distance factor, dipole moment of 2 should be greater than that of 1, followed by 3, followed by 4, right? Leave 3, 4 aside. We just have to compare 1 and 2. As per charge factor, this has to be the order. As per distance factor, this has to be the order. And in case of CH3F and CH3Cl, distance factor dominates over charge factor. And when distance factor dominates over charge factor, the dipole moment of CH3Cl will be more than that of CH3F, then your CH3Br, and then your CH3I. Am I clear? Am I clear with this? Quick, people. Let me know in the chats. Yeah? I believe this is clear. Now, guys, look at these 4 molecules which are given to us. We have to say which has maximum dipole moment. Which of the 4 has got maximum dipole moment? Which of the following has got maximum dipole moment? Quick, people. How do you solve this sort of equation? Just try to understand this. Understand this properly. First of all, if you look carefully, this is CF bond. CF bond. Which one is more electronegative? Fluorine. So fluorine will attract the bond pair towards itself, negative, positive, right? So this is going to be the direction, right? Positive to negative. Positive to negative, positive to negative. Let's assume this bond moment is X, this bond moment is X, this bond moment is also X, right? Now, one vector pointing upwards, one vector pointing in this direction, one vector pointing upwards, one vector pointing in this direction. This is X, at an angle of 120. The resultant will be here. X and X at an angle of 120. Resultant will be how much? Resultant will be x only. So resultant of this and this will be x in this direction. Already there was x in this direction. Now the resultant of these two, that's also x, which is in this direction. So x plus x makes it 2x. Do you understand this? Do you understand this? X and x. Guys, this is something which you study in physics. Let's say you've got one force in this direction, one force in this direction. F at an angle of 120. The resultant will be in this direction. It will be also F. Right? This is something which you would have studied in physics, right? Simple. Look at the second case. Positive to negative. Positive to negative. Positive to negative. Correct? Now, this moment and this moment, they are at an angle of 120. Right? If this is x, this will be also x, this will be also x. Now, the resultant of these two will be in this direction, that will be also x, and this x will get cancelled out. So net here is 0. Net dipole moment here is 0. Correct? Look at this particular case. Positive to negative, x, positive to negative, x, positive to negative, x. So this x and this x will get cancelled out. So resultant in this direction, that's x, right? So that is the resultant here. Now, positive to negative, cancel out, net is 0. So tell me which one has got maximum dipole moment. The net dipole moment here is 2x, here it's x, here it's 0, here it's 0. So A is going to be the correct answer of this particular question. Yeah? Am I clear? Am I clear, people? Am I clear? Quickly let me know in the chats. One more thing, guys. One more thing. Tell me what will be the net dipole moment here and what will be the net dipole moment here. I just want to know. Is it going to be 0 in both the cases or not? Is it going to be 0 in both the cases or not? Quickly. Quickly, guys. Quickly. Yes, Jack Sparrow, you can go to some other channel, bro. Not here. Okay. Jack Sparrow. Wow. Tell me, guys, where do you see the net dipole moment 0? Is it 0 in both the cases or in just one? See, in this first case, it's going to be from CL is more electronegative, so delta negative, over here delta positive. So from positive to negative, again from positive to negative. Cancel out, net is 0. Net is 0 here. But here is not going to be 0. Here is, no doubt, you're saying OH at the top, OH at the bottom. Don't think that they'll cancel out. Because the orientation of H over O is different here. See, just to make you understand, just so that you can remember it, if you talk about this OH, which one is more electronegative? Oxygen. So negative, positive. So positive to negative. Similarly, positive to negative. Do you see they're cancelling out? They're not cancelling out. So net dipole moment here is non-zero. Net dipole moment here is non-zero. Remember this particular case as well. Okay? Remember this particular case as well. Now, tell me the answer of this particular question. Read the question carefully and tell me the answer. Which of the following set of molecules will have zero dipole moment? Which of the following set of molecules will have zero dipole moment? Quickly. Quickly, guys. BF3, HF, CO2, 1,3-dichlorobenzene. NF3, BeF2, water, 1,3-dichlorobenzene. BF3, BeF2, carbon dioxide, 1,4-dichlorobenzene. Which one? Quick. Quick, guys. It has to be option C. It has to be option C. Why is that? So first of all, if you talk about your BF3 molecule, your BF3, this is boron, fluorine, fluorine, and fluorine, right? So this bond, fluorine will be negative, boron will be positive. So positive to negative, positive to negative, positive to negative. If this is X, for example, this is X. Now these two vectors, they're at an angle of 120, they're resultant in this direction, that will be X. So this X gets cancelled out. So net dipole moment is 0. So BF3, net dipole moment is 0. Now BEF2, this is something which we discussed in the beginning itself. This is BEF2. Its net dipole moment automatically 0, right? Positive to negative, cancel out. Carbon dioxide, this is also which we discussed in the beginning of the dipole moment. Positive to negative, cancel out. This 1,4-dichlorobenzene I showed you a few minutes back only. 1,4-dichlorobenzene. Its net dipole moment we discussed in the beginning itself, right now, 5 minutes back. So its net dipole moment is also 0. So it has to be option C, which is going to be, right? Which is going to be, yeah, clear. Right? Right, people? Wow, yes, correct. You're right. That's why I'm here from past 6 years on YouTube. 6 years back, that organization was not there, by the way. Yeah. I believe I'm clear. I believe I'm clear. I believe I'm clear. Yeah. Perfect. Perfect, perfect, perfect. So with this, people, the dipole moment concept is over, and the next part, that's going to be the theories involved, which is VBT, VSCPR, MOT. That's something which will be discussed in the next session, right? I've got basically one more session coming up exactly at 9. Okay, that is the droppers batch, which is the paid batch. So I'll have to take a leave right now. I'll see you guys exactly on Tuesday at 7 p.m. And on Tuesday, 7 p.m., we shall be completing the whole chapter, the rest of the things. Yeah? Perfect. Chalo, do let me know in the comment section of this particular video how you find it. I think all the types of the questions which were here, right? All the types of the questions which can be asked from your Fajan's rules and the dipole moment are done and dusted. Perfect. The next session is going to include your VBT, VSCPR, MOT, and we shall be completing the chapter in the next session. Okay? Perfect. Chalo, I'm stopping with this. I'll see you guys all in the next session. Do let me know in the comment section